Hi, everybody, and welcome to today's edition of the Spectral Geometry in the Clouds seminar. So today we have the pleasure of having Sasha Pushnitski from King's College, who will talk to us about the spectra of some arithmetical matrices. Sasha, the floor is yours.
Thank you very much, John. Thank you. It's a real pleasure to speak at this seminar, real pleasure to see familiar faces. This topic was a bit of a kind of a aside for me from my main activity, but I found it very enjoyable to learn a little bit about number theory and other subjects. And so I'm not an expert in this topic at all, but I hope you will find it entertaining. So this is joint work with Titus Hilberding, who, in contrast to myself, he is a number theorist. So he was in Reading when this work was going on, and now he moved to China, to Nanjing. Okay, so what are arithmetical matrices? These are matrices whose entries have some sort of arithmetical significance. So they have to do with least common multiple or greatest common divisor or something like that. So let me start by just very easy introduction, just to remind you the definitions of the basic objects. So and notation. So for n and m natural numbers, I will denote by these normal brackets the greatest common divisor of n and m, and by square brackets the least common multiple of n and m. And just to remind you, we have the fundamental theorem of arithmetic. So every natural number can be represented through product of powers of primes. And I will write it in this way. So Kp is a kind of multi-index labeled by prime numbers. P is always prime here. Now suppose if we have two natural numbers n and m, then one will be labeled by multi-index, one corresponds to multi-index Kp, another corresponds to multi-index J. Then if we multiply them, then in terms of K and J, of course, we will have additive notation. And then the greatest common divisor corresponds to taking the minimum between K and J for every component P. And the least common multiple corresponds to taking the maximum between K and P for each prime P. Okay. In particular, from this formula, you see that if you multiply the GCD and LCM, what do you get? You get the sum of the smallest and the largest between K and J, which is the same as taking J plus K. So you get exactly the product of NM, well-known formula. Okay.
Sasha, do you mean to share the screen?
Am I not sharing screen? Sorry.
I don't think so.
The screen is shared for.
I can see the screen. Yep.
Oh, okay.
I can see perfectly. So.
Sorry. As they say in Bulgarian, the problem is in your television. So I don't know. So we are interested. So we are interested in these GCD LCM matrices. So what are they? They are matrices where the entries, nmth entry involves the GCD of nm or the LCM of nm. So sometimes this big N can be finite, or sometimes it can be infinite, depends on the context. So it's a kind of a loose definition. So you should think about this as a kind of multiplicative versions of matrices where the nmth entry is a minimum of n and m or maximum of n and m, right? Because of this formula. So I've prepared some pictures for this. So this is done in Mathematica. So this is the LCM matrix. It shows color plot. So the color corresponds to the magnitude, and this is the maximum of n and m. So if you see that for this maximum of n and m matrix, the constant elements on these L-shaped lines, kind of broken lines, right, like this and like this. And for GCD, of course, it's a rather complicated pattern, as we see. So this is purely for your visual enjoyment for the moment, and just to show that they're quite different beasts. Okay. Now, let me talk a little bit about the history of this subject. So the genesis of this topic is Smith's determinant. So Smith was a professor in Oxford, and at some point, I don't know why, he decided to compute this determinant. So you take an n by n matrix made of greatest common divisor of n and m, and he computed this determinant. It turns out that there is a closed formula for it, this product, where phi is Euler's tangent function, which is the number of integers up to n relatively prime with n. So we will not need this formula. This is just to explain the origin of this subject. And so after his paper, these matrices became known as GCD matrices, and their counterparts became known as LCM matrices. For a number of years, further literature on this was mostly algebraic. So for example, people looked at such matrices not between 1 and n, but over some subsets of n with some structure. They asked about invertibility, positive definiteness, some factorization, and so on. So it became a kind of a little discipline on the cusp between algebra, number theory, and linear algebra. Then you can also study a power GCD LCM, which means that you raise every element to the power. So some power at this point can be any real number. And let me just notice that from this point of view, GCD and LCM matrices are algebraically equivalent. Because of the formula we saw on the previous slide, I can always rewrite LCM matrix in terms of GCD times some components here, and these components correspond to just multiplication by diagonal matrices. So algebraically, they're kind of trivial operations. At this point, let me just mention positive definiteness, which was worked out quite early, that GCD matrix is always positive definite for if the power is positive. And from this formula, it follows that the same is true for LCM if the power is negative. Okay. So this was kind of the first, I should say, origin of this subject. Now, to describe the second origin, for a moment, I have to digress and talk a little bit about Hardy space and Hardy space of Dirichlet series. Okay. So let's start with the classical Hardy space. This is the space of functions analytic in the unit disk. And it's defined as the space of all power series of this form, where the coefficients are square summable. And you should think of z as a variable inside the unit disk, but if you wish, you can also go to the boundary and think of this function, this as a Fourier expansion of your function on the circle. Now, let's now consider the following scenario. Let's take a function which is called symbol in this context, which is, let's say, bounded function on the unit circle. So here I allow the indices n to go from -infinity to infinity. We are on the unit circle. And now consider the following thing. I want to look at the matrix of multiplication operator by phi restricted to the Hardy space H2. So I forgot to say that the Hardy space H2 can be considered as a subspace of the L2 on the unit circle. So if you do this, if you consider this, let's compute the matrix of this operation. So you multiply phi by Zn. So here Zn is an element of the standard basis in the Hardy space. And then you take in the product with Zm. So you see that as a result, you get phi m minus n. Right? So the important here is that you have this m minus, the minus structure. So a matrix of this form, where the nth element depends on the difference m minus n, is called a Toeplitz matrix. And one of the fundamental facts in the theory of Toeplitz matrix is that the essential spectrum, in fact, absolutely continuous spectrum, well, if let's say phi is a real valued function, then the absolutely continuous spectrum of this operator of this infinite matrix is precisely the range of the function phi. Okay, so this is a kind of classical theory. Now let's move to a Hardy space of Dirichlet series. So possibly for the lack of imagination, it's also called H2, but the H is curly H2. So what is it? It's a space. If the standard Hardy space is built on power series, this space is built on Dirichlet series. So you take an arbitrary Dirichlet series, and you require that the coefficients are square summable. This gives you a certain norm on this space. It becomes a Hilbert space. And by Cauchy-Schwarz, you see that this function will be analytic in the half plane where the real part of S is greater than 1/2. So this half plane plays a similar role to the unit disk in the standard theory. Now, in the same way, let's talk about Toeplitz operators. So here, I don't want to get too much fixated on the class of the symbols. So let's say it's just a Dirichlet polynomial. So only finitely many phi n's are non-zero. And then we do a similar kind of calculation. So we take, so this n to the minus s, this is a standard basis in this Hardy space of Dirichlet series. And we compute the matrix of the operation of multiplication by phi with respect to this basis. What we get is phi m over n if n divides m, and if it does not divide m, then it's 0. So this is a kind of similar structure to the classical Toeplitz matrix, but instead of minus, you get divided, right? So instead of additive structure, you use the multiplicative structure of integers. And so matrix of this form became known as multiplicative Toeplitz matrix. More or less mimicking the standard theory, you can prove that the essential spectrum of this multiplicative Toeplitz matrix corresponds to the values of your symbol on the imaginary line. Here I'm assuming that it's a Dirichlet polynomial, so it makes sense to take it on the imaginary line. So the origin of this subject actually goes back to the paper by Toeplitz himself. He published this paper, I think it was his last paper maybe, or it was at least a year before he died. And but it was well forgotten by the community. And then the subject was rediscovered by Hedenmalm, Lindqvist, and Seip in 1997. So basically, I can say informally, the paper was an attempt for analysts to engage with number theory, with analytic number theory. Because, you know, what do? We do function spaces in analysis, and they try to build a function space that speaks to analytic number theory, that is relevant for analytic number theory. And in some sense, they succeeded. So now I want to come back to the LCM GCD matrices. Okay, so let's consider the following symbol. Let's take the symbol, which is just the Riemann zeta. So let's take sigma. Sigma will be an exponent greater than 1, and take phi n, just n to the power minus sigma. Okay, and then I write down the Dirichlet series expansion for the Riemann zeta function. And now I consider this, I regard this as a symbol. Okay, I know it's not a Dirichlet polynomial, but let's be generous. Okay, let's just imagine we consider the operator, the multiplicative Toeplitz operator, whose series of coefficients is given by this formula. So then you can check that, so this will be non-self-adjoint, but if you consider this kind of self-adjoint version of a T star T, then its essential spectrum will be precisely given by the values of Riemann zeta on the line with the abscissa sigma. So this is precisely the analog of the classical Toeplitz operator theory. Now, of course, if sigma becomes less than 1, we are in the critical strip. So the zeta function becomes unbounded. Here, purely for your visual enjoyment, I've plotted the graph of absolute value of Riemann zeta for sigma corresponding to 3/4. You see it's a intricate pattern. It has some small values and some large values. So sigma becomes unbounded and the Toeplitz operator becomes unbounded. Now, let's ask the question. Okay, both things are unbounded, but maybe the truncations of the matrix correspond to restrictions, in some ways correspond to restrictions of zeta onto finite intervals. Maybe if T corresponds to N in some ways. This is kind of the idea that was hanging in the air maybe 10, 15 years ago, let's say. So I'm not qualified to tell you about the results of this inquiry, but let me just say that many people contributed to this. So in some form it was known, some aspect of it was known as Saunder-Rajah's resonance method. My collaborator, Titus Hilberding, contributed to this, and then it was picked up by other people, and there was some work in this direction. Now, when you do this, I want to get back to this GCD LCM matrix. So let's, for a second, let's go back to sigma greater than 1 when this series converges and all these operations are completely legal. So then when you can compute T star T, you get some constant, and then you get this matrix E, which is precisely this weighted LCM GCD matrix. You can write it down in two equivalent forms, like this or like that. Okay. So this matrix became known as Gall's matrix. And its minimal and maximal eigenvalues of it, of some suitable submatrices, became an active area of research. And in particular, this line of inquiry contributed to some results on behavior of Riemann zeta on vertical lines in the critical strip. Now, this was all, this is a kind of another source of interest to these GCD LCM matrices. Now I'm coming to the main story, to the main hero of my story. My collaborator, Titus Hilberding, he decided to look at these, okay, let me go back one page, to this Gall's matrix, but freeing up the parameters, the powers on top and at the bottom. Here they are rigidly connected, right? This sigma here and 2 sigma here. But imagine I have one parameter here and one parameter on the top. And let's just look at this as a question, as an object of operator theory. So that is what is written here. So here we have this weighted GCD LCM matrix. We have two parameters, tau downstairs and this sigma upstairs. So clearly this is a formally self-adjoint matrix. And the question is, let's consider it as an operator on little L2. And let's study its operator theoretic properties. So let me start by making an important remark that this matrix has an important homogeneity property. If I multiply n and m by the same integer k, I get there's 1 over k to the power rho, where rho is tau minus 2 sigma. So this rho is an important homogeneity parameter, which I will use in what follows. So in fact, you can, okay, we have 3 parameters, tau, sigma, or rho, and you choose any 2 of them to parameterize your family. So it depends on the situation. Usually I will choose tau and rho. Okay, So let me make a few remarks about operator theoretic properties of this guide. So my talk is about these weighted GCD LCM matrices and what operator theoretic properties does it have. First of all, it is positive definite. This is purely algebraic, and this is equivalent. It's positive definite if and only if tau is non-negative. And this is purely algebraic. It does not depend on sigma at all, because as I said, these n to the sigma, m to the sigma correspond to multiplication by diagonal matrices on the left and on the right. And so they don't change positive definiteness. So this is purely algebraic property. Next, let's discuss boundedness. So imagine we want to test the boundedness of this operator. So the first simplest thing to do is to try to take the first, let's take the first vector of the standard basis and act by this matrix on this vector. What do we get? We get this thing, right? So we get m becomes 1, and we get n to the sigma from the top and n to the tau to the minus tau from the bottom. So you get this vector. So for this operator to be bounded, you better have that this thing is an L2, obviously. Otherwise, boundedness breaks down. And so this means that sigma minus tau has to be less than -1/2 for this to be square summable. If you rewrite it in terms of rho and tau, this becomes rho plus tau greater than 1. So that's a constraint for boundedness. Now let's do another simple test. Let's look at the diagonal of our matrix. On the diagonal, what do we have? On the diagonal, we have precisely, so if we look back to this homogeneity condition, on the diagonal, this part is 1, n sigma, we just get 1 over n to the rho. This is what we get on the diagonal. And so for this matrix to be bounded, this rho should be positive, because otherwise we will have, if we have growing entries on the diagonal, clearly such matrix cannot be bounded. So we have identified two conditions necessary for boundedness. Rho is positive, greater than or equal to 0, and rho plus tau greater than 1. So it turns out that this precisely describes conditions on boundedness. So let's just ignore boundary cases. So here on the graph, on this diagram, I've plotted. We have the shaded region corresponds to the intersection of these two conditions. Rho is positive, and rho plus tau greater than 1. So turns out, let's speak about the open shaded region. Then this is precisely where E is bounded, and in the open shaded region, it's automatically compact. In the complementary region, it is always unbounded. So we have precisely described where this matrix is bounded and compact. So Gall's matrix, so what number theorists are interested in, corresponds to rho equals 0, and in fact, the critical strip corresponds to this line between 1 and 0, okay? So it's certainly where the matrix is unbound. And as an operator theorist, in the first instance, I'm interested in what happens for bounded and compact case. Okay, so let's discuss it. So there are two results. So it turns out that the analysis is different in up here in the upper part of this shaded region and in the lower part. Okay, so let me start with the upper part. So this corresponds to tau being positive. I already said that tau being positive or negative corresponds to this matrix being positive, definite or not. And turns out that the results are completely, the spectral structure is completely different in both cases. So let's start with the positive definite case where tau is positive. So we are in this darker shaded region up here on this picture. So this is just a reminder that the homogeneity is minus rho and rho is tau minus 2 sigma. So we consider the upper part. So here's the first theorem. So in these conditions, so let tau be positive. So we are here, rho also is positive and tau plus rho greater than 1. So these three conditions describe this darker shaded region. Then our matrix is bounded, compact, positive semi-definite, and for the eigenvalues, we have the following asymptotics. So we have some coefficient kappa here, and then the leading term of the asymptotics is kappa over n to the rho. So notice that this precisely corresponds to the asymptotics of the diagonal elements of the matrix E, right? So the diagonal elements, as I discussed on the previous slide, are 1 over n to the rho. And so here we have the same order, but the coefficient, turns out the coefficient doesn't have to be 1. So we were able only to compute the coefficient kappa in two particular cases, when rho equals 1, in this case it's 1, but interestingly for rho equals 1/2, there is some sort of, explicit, but it's not 1. Explicit formula, but it's not 1 for this coefficient. It clearly has some arithmetical significance. Okay, so, and I'm not a numerical analyst, but specifically for this talk, I decided to compute the eigenvalues of this matrix. So I've truncated this. So the simplest case where sigma upstairs is 0, so there is no sigma, and tau is 1. Okay, simple matrix. I've truncated it to 10,000 to 10,000, and I looked at the counting function of eigenvalues. But of 1 over lambda. So lambda n should be asymptotic to n. So I looked at 1 over n, this should be asymptotic to n. So yellow line is just lambda equals n. And this is the thing. So this is the counting function. So you see it's a pretty good fit. Okay. So now let's move to the other case when tau is negative. Tau is negative. So then, as I said, so I'm just repeating here the basic information about this matrix. So when tau is negative, we are talking about this triangle in the lower half plane. So in this case, the positive definiteness breaks down. And so our matrix is not necessarily positive definite. By the way, you can see it already by looking at the top left 2 by 2 submatrix. Already this one will not be positive definite. So it's very easy to see. So here's the second result. So let tau be negative and tau plus rho greater than 1. That precisely describes this triangle. Then the matrix is bounded, compact, and it has infinitely many positive and infinitely many negative eigenvalues. So it's not just you get a few negative ones, you get infinitely many instantly. So now if we denote the positive ones by lambda n plus, order them monotonically, and the negative one by lambda n minus, again by minus lambda n minus, right? So then you see that these two sequences have exactly the same asymptotic. So that means that the spectrum becomes kind of symmetric, asymptotically symmetric. It's not exactly symmetric, but up to the first term, it's asymptotically symmetric with respect to reflection around 0. Okay, so the structure of the spectrum changes radically. Okay.
I'm sorry, Sasha, do you actually know that it's not symmetric?
I do, yes, we do, because yeah, I will comment on this later.
Okay.
Yeah, this is asymptotics. So
sorry, Sasha, isn't there a minus in the second identity?
no, so I define the negative eigenvalues by lambda n minus. So lambda n minus the absolute value of the negative eigenvalues. Okay. So a few comments. So it's a different exponent. In the previous slide, I had 1 over n to the rho. 1 over n to the rho. Here is 1 over n to the rho plus tau. So the exponent changes continuously as you go through this line, but you know, it's a different exponent. Upstairs is rho, downstairs is rho plus tau. Unfortunately, we don't have any formula for the asymptotic coefficient kappa. We are not able to compute it for any value of rho. And I think it's an interesting problem. I want to compare these results that I've just outlined. So these are for, so as I said, these matrices have a kind of multiplicative flavor because the elements are least common multiples. I want to compare them with their additive cousins. Sorry, I'm going wrong direction here. So let's consider the following setup now for comparison. Let's consider continuous integral kernel of two variables, x and y, which is formally self-adjoint, and it's homogeneous of degree rho, minus rho. And now let's restrict this kernel onto integers. And then we get this matrix. Important remark, our matrix, this LCM, is not of this family, is not in this category, because you cannot write down this as a homogeneous, as a continuous homogeneous function on real numbers. It doesn't work, but it looks a bit similar, you know, it looks a bit similar, and so it's instructive to compare. So here are some examples. So for example, the Hilbert matrix, so its scaled version is in this category with the rho as a power. And this is the matrix depending on the maximum of n and m. And this is its scaled variant. So this is a bit like the additive variant of the matrix E that I considered on the previous slide. Instead of the LCM here downstairs, I have the maximum, right? So it's the additive version of LCM. So now if we look at the spectral properties of these of such matrices, of this whole class, you see the following picture. If rho is between 0 and 1, this matrix is unbounded. If rho is 1, it's bounded but not compact. And the study of its continuous spectrum is an interesting problem. And if rho is greater than 1, immediately it becomes compact and trace class. So rho equals 1 is a kind of threshold. So it cannot be, for example, compact but not trace class, right? It immediately falls down into this trace class category as soon as it becomes bounded, as soon as it becomes compact. It's a very different story from what we saw for our LCM matrix. So let me show them side by side. Okay, so this is the additive version, and this is the LCM version, right? So for the LCM version, we can have asymptotics. Remember that upstairs here, the asymptotics of eigenvalues is 1 over rho. So rho can be very small here, for example. Rho can be very small, and so the matrix may be compact, but not trace class, let's say. And here, this is the boundedness region for this guy, and immediately you fall into trace class category. Okay, now I want to make a little aside about L matrices. So it's not strictly speaking about the same topic, but because I've mentioned matrices depending on the maximum of n and m, I wanted to talk about this a little bit, particularly to popularize this interesting class. So a matrix which depends on the maximum, whose nth element depends on the maximum between n and m, is called an L matrix. So L because the constant elements live on these L-shaped kind of lines, you know, this is how it looks like, the entries of an L matrix. For comparison, Hankel matrix, for a Hankel matrix, constant elements are on these lines, orthogonal to the main diagonal, and for Toeplitz one, they are on these lines, parallel to the main diagonal. So all of these three matrices are examples of structured matrices, where we have some specific structure. So these L matrices are relatively recently, they came to attention. There was a nice paper by Choi called Tricks and Treats with the Hilbert's matrix. It's full of interesting stuff. So he called this matrix the loyal companion to Hilbert's matrix, and he used it to prove something about it. Then Buthat and Mashregi looked at norms of this matrix and some variations of this. And then František Štampak, who is here, he considered general L matrices, so matrices of this form. And he made an important observation, which is key to this, that all such matrices are inverses of Jacobi matrices. So let's assume, more precisely, let's assume that Ln minus Ln plus 1, right? So L is this sequence. So it's the defining sequence of this matrix. So this is L1, this is L2, this is L3, and so on. So let's assume that this difference Ln minus Ln plus 1 does not vanish. Then he called such matrices non-singular. Then let's define this sequence Bn. And then, at least formally, let's not worry about the technicalities. If you take the inverse of the L matrix, you get a Jacobi matrix. And so using this idea, you can analyze many of these L matrices. Okay, now let me come back to my E matrices, the arithmetical matrices. So I want to give kind of some idea of the proof of the main results and at the same time explain the structure. So here I put this E matrix in the simplest case when sigma equals 0, you know, the sigma were the upstairs powers upstairs. So let's, for simplicity of this formula, let's just think of this matrix. Okay, so once again, if I have the prime factorization of n in this form and the prime factorization of m in this form, then the LCM is can be written in this way. And so the nth element of my matrix, I can write it in this way. So at least formally, it means that I can write down my matrix as an infinite tensor product of matrices of this form. So think of primes as kind of labels. They label variables, right? So these Kp and Jp, they're multi-indices with many, many, many coordinates, infinitely many coordinates. And so I see that in terms of these coordinates of K and J, I have a product, which means I have a tensor product of matrices. So this formula really is key to understanding the spectral structure of E, at least for us, for me and my collaborator, this is what we did. Observe, by the way, that this factor matrix, EP, is an L matrix, right? It depends on the maximum of K and J. And this was also important in our analysis. Now, from this tensor product formula, at least formally, you get the corresponding eigenvalue product formula. So what does it mean? So imagine, okay, let's step back. Just I want to explain it in a really, really elementary way. Imagine you have a tensor product of two matrices. So what does it mean about the eigenvalues of this tensor product? It means you take all possible eigenvalues of these two matrices and multiply them, right? And all possible products, this will give you the spectrum of the resultant matrix. So the same story is here. So you have to take all possible eigenvalues of each of these EP matrices, and you have to take all possible products of them. And it's just a question of labeling it in the right way. So let's say so the exact theorem is this, that there exists an ordering of eigenvalues of E such that they can be written in this way. For each n, you write down its factorization in this way. Then you take the corresponding Kp, and then for each p, you take the corresponding kpth eigenvalue of EP. Then you multiply them in this way, and you get the eigenvalue, the nth eigenvalue of E. So this is what part of what we prove, but it's based on this factorization, on this simple identity. In particular, it means that if you want this to make sense, then lambda 1 of EP should better converge to 1 pretty fast, because otherwise these infinite product will not converge. And this is indeed the case. Okay, so now based on this, the idea of the proof was the following. We look at this EP, and we notice that this EP, the pth term in this product, it's an L matrix, but it also has an interesting self-similar scaling structure. If you write down, you write down the first row and first column, and here everything else. Then you observe that this everything else is the scaled version of the full matrix. So you delete the first row and the first column, and what you get up to scaling is the full thing. It's a very pretty structure. So based on this structure and just on linear algebra, we proved that the kth, so if you fix P and you look at the kth eigenvalue of this EP, then it obeys these asymptotics. It's power asymptotics. It's exponentially going to 0, plus some error term, but let's not worry about it. So it's exponentially going to 0 because when you go to the next level, you are scaled by fixed factor. So it's this factor gets multiplied by itself k times when you go down k times. Okay, and then the heuristics behind the main result is very simple. Let's take this eigenvalue product formula. Okay, and now let's formally replace this lambda k by these asymptotics. Let's just ignore the error term now. Let's just replace it by the asymptotic. So what you get is this. And then you notice that by rearranging this is exactly, you take the product of this p to the kp, and that's exactly n to the tau. So you recover these asymptotics. Of course, you don't recover the coefficient. Okay, these heuristics is cheating you at this level. It just gives you the correct order, but the error term hides formula for the coefficient. So more rigorously, what we do, we consider these kind of moments of eigenvalues, if you wish, right? For a fixed S, you consider these kind of moments of eigenvalues, or this is what it is, or traces of S power of E. And because of this eigenvalue product formula, they can be rewritten, they can be factorized as products of the corresponding objects for the EP matrices. And then we have to analyze their behavior analytically as functions of complex variable S. They will have some analytic continuation to a certain strip. They will have poles somewhere, and these poles will determine the asymptotics of at least the first term of the asymptotics of them. That's the construction. One interesting thing that I wanted to mention in connection with this is that there is an interesting kind of reflection formula that relates positive tau and negative tau. So once again, here is the formula for the full matrix, now with the sigmas. So it's a infinite tensor product of these matrices, these EPs, and these are these matrices in the product. Now, for tau positive, all of these component matrices EP are positive semi-definite, and so the full matrix is also positive semi-definite. Now, what happens for negative tau? When we go from this region to this dark triangle, what happens there in this dark triangle? So if we are there, this is the conditions describing this dark triangle. Let's take notice of the following elementary formula. If you have two integers, then this, if you add the maximum between these two integers and the minimum between these two integers, you get the sum of these two integers, okay? Not very clever. Then you apply this to this, because this is what the main component of this EP. I'm ignoring the numerator for the moment. I'm just looking at the denominator. So I have 1 over p to the tau maximum, 1 plus 1 over p to the tau minimum. This is the same as this, right? One of them will be maximum, another one will be minimum. Then I'm applying the same formula again. I'm here in this term, I have the minimum, and using this formula, I'm swapping the minimum for the maximum. I'm swapping the minimum for the maximum, but I will have these extra factors, diagonal factors. Then in the end, if I multiply by the numerator, I get the following formula that EP for tau and rho is the same. See, here I have tau, and here I have minus tau. So I've swapped tau for minus tau, but in the right-hand side, I have some rank 2 operator. This is just the sum of two operators which are rank 2, because this depends only on k, and if I multiply by this, I still get rank 2. And so in the end, I see that for negative tau, here I have the operator with a minus tau, which is, positive parameter, plus some rank 2, which means that my component matrices here will be negative except for possibly rank 2, some rank 2 thing, because this will be negative definite with a minus, right? Negative definite. So as a result, I see that all eigenvalues for this value, for negative tau, all eigenvalues of EP, in fact, you can check that this rank 2 will only create one positive eigenvalue. So all eigenvalues apart from 1 are negative. This is what we get. And then you start taking tensor products of this, and then, everything gets mixed up, the positive and negative components. And this creates this kind of almost symmetry of the spectrum, asymptotic symmetry of the spectrum. This is what we get. So basically, our work is a bit of linear algebra with these EPs and then putting them together in the right. Okay, this is my thank you slide with a pretty picture of Gall's matrix for sigma equals 1/2. Just a beautiful pattern that I wanted to display. Thank you very much.
Thank you, Sasha, for your nice talk. So if there is any question or comment, you can unmute yourself or put it in the chat.
So, can I make a question or comment?
Yes, Igor.
Yeah. So in fact, it's like semi-question, semi-comment. I see, as you pointed out, this is a very beautiful picture. And it looks a little bit fractal-like, and also your recursion, it looks a little bit fractal-like. Can these two be related?
You mean this one?
Yeah.
This one is for for EP, for the fiber mate, for one element in this product. So it's hard for me to say. I think going back to this one, I'm not sure it's fractal. I cannot comment really. I cannot comment.
So as I said, it was like semi-question.
Maybe you're right, but yeah.
It looks like it's of the same spirit, but I wouldn't be able to.
Hi, can you hear me? Yeah. So since the asymptotics, positive and negative, look similar, maybe there is a underlying symmetric matrix, operator with actual symmetry of which the operator is a small perturbation. Can you guess something like this?
Well, you see, this last discussion was precisely about this. That up to rank 2 term.
Okay.
Up to rank 2 term, it's precisely what is happening. But, it's not exact. There is this rank 2 term.
No, but that answers my question. Thank you.
Yeah.
Sasha, but if you didn't have this rank 2 term, then the Oh yeah, so for each EP it would be negative, and then you get products of positive, negative numbers, and
Yeah.
yeah,
It's-
but yeah, but for EP you say that there is one positive eigenvalue, and I
so
guess
this
it would be better to be close to one when P is large.
exactly. So the story is like this, that you'll have one positive eigenvalue, which is going to be close to one, and then one negative eigenvalue, which will be a bit like p to the minus this power that we have, p to the minus rho plus tau. Then when you start multiplying them, you see this pattern.
Okay.
You see this pattern. As far as I am aware, it's not exact. Of course, there may be something else that we're missing, that there may be nevertheless, some underlying exact symmetric structure, but I very much doubt it. It seems that we see what's going on.
Sasha, I'm talking about the first theorem, the case where everything is positive, tau positive, rho positive, etc. In this case, is there some hope to improve the remainder term here, the small o of n to the minus rho?
Yes, so this is where my my powers ended, but my collaborator found a paper in number theory using which he improved it just a little bit. It was exponential to minus, so it will be n to the minus rho multiplied by exponential to minus square root of log n or something like this. So it's something very weak, but it requires quite strong input from number theory.
Okay. Interesting. Thank you very much.
So yeah, I had so you said that as someone who does operator theory, you were interested in the bounded and compact situation. But let's say I want to know about the unbounded situation. Do we know anything about them? Do they have compact resolvent, for example?
It's a great question. I think it's open. It's completely open. I think also intermediate case is quite interesting, right? When you are bounded but not compact. And I looked at it a little bit in the context of these homogeneous. Where are they? Yeah, these homogeneous matrices, because this is an interesting case. So I looked at this case a little bit.
Yeah.
So no, the answer to your question is no. Nobody looked at it, but yeah, it's open.
Okay, any other questions or comments? Okay, if not, let's thank Sasha again. And so we reconvene next Monday. So the talk will be by Jad Brisson on Steklov eigenvalue of negatively curved manifold. Okay, see you next week. Thank you.
Thanks a lot, Sasha.
Bye.
Thank you.
Thank you.